A penguin, an egg, and an asteroid collision. This week on Planetary Radio. I'm Sarah Al-Ahmed of the Planetary Society, with more of the human adventure across our solar system and beyond. Last week on July 12th, 2024, we passed the second anniversary of science operations for the James Webb Space Telescope, or JWST. We're marking the occasion with a dive into its newest beautiful image, a close-up of a region called the penguin and the egg. Christine Chen, associate astronomer at the Space Telescope Science Institute, tells us about the image before returning to tell us more about her team's recent findings in the Beta Pictoris system, where clearing dust indicates a recent and powerful asteroid collision. Then we go back to the early solar system with Bruce Betts, our chief scientist, as we discuss the massive collisions that shaped our place in space and what's up. If you love Planetary Radio and want to stay informed about the latest space discoveries, make sure you hit that subscribe button on your favorite podcasting platform. By subscribing, you'll never miss an episode filled with new and awe-inspiring ways to know the cosmos and our place within it. The James Webb Space Telescope's journey began with a flawless launch in December of 2021. And the mission has been such a massive success ever since. It was built on the success of previous space-based observatories, and it's changing the way that we study everything from the youngest galaxies in the universe to the planets in our own stellar backyard. To commemorate the second anniversary of science operations for the telescope, NASA unveiled a gorgeous new image captured by JWST. A new picture of a pair of interacting galaxies known collectively as ARP-142. It's a region space fans lovingly call the penguin and the egg. The Penguin Galaxy, or NGC 2936, has a distorted shape that looks a lot to Earthlings like a star-studded penguin that's protecting this elliptical galaxy right nearby called NGC 2937. That elliptical galaxy looks like a small oval shape, like an egg. So together, the Penguin Galaxy and the egg make this beautiful but also very adorable image. Joining us today to discuss JWST's new image is Dr. Christine Chen, an associate astronomer at the Space Telescope Science Institute. Christine is actively involved in shaping JWST's scientific endeavors as a member of the Space Telescope Science Institute's Science Mission Office and as the JWST Science Policy Group Lead. The Space Telescope Science Institute is the space operations center responsible for managing and distributing data from the observatory. During this conversation, you're going to hear Christine refer to a point in space called L2. That's the second Sun-Earth Lagrange point where JWST orbits. There, the Sun and the Earth's gravity balance out in a way that allows the telescope to permanently keep the Sun, Earth, and Moon at its back so it can observe space in infrared light. Christine's expertise lies in studying the formation and evolution of planetary systems, particularly focusing on the properties and distribution of dust and debris disks around stars. Hi, Christine. Welcome to Planetary Radio.
Hi, thanks for having me.
So to celebrate the second year of science operations for JWST, the team just dropped this beautiful new image. Can you tell us about it?
Absolutely. This gorgeous image, it shows two galaxies that are close enough together to interact with one another. We think that they first passed by each other about 25 to 75 million years ago, and we expect that they're going to continue on with their cosmic dance with one another for millions more years. The galaxy on the right is called the Penguin. It looks like a penguin, and it actually used to be a spiral galaxy just like the Milky Way. And when it passed close to the galaxy on the left, which is called the egg, it became wildly distorted. So if you look really closely at the eye of the penguin, it actually used to be the center of the spiral galaxy, and the beak and the back of the penguin used to be its spiral arms. So you can kind of tell that this beautiful structure of spiral galaxies that we see, it's actually quite delicate. And so it's easily torn apart when the spiral galaxies encounter other galaxies. The galaxy on the left, the egg, is called an elliptical galaxy. And these are more dense and compact, so they're more like a cannonball. And so they're difficult to change shape when they interact.
Why was this the image that was chosen to celebrate this anniversary? Because JWST has created so many iconic images at this point.
I think the way that the images or the targets are chosen is a combination of reasons. One is that we already have some information about the sky, and so we can kind of guess what we think will look beautiful. and, where JWST will be able to provide some complementary information. For example, I talked about how I think for JWST, one of its superpowers in the infrared is being able to see through dust. And so that means that, if we see a really beautiful star-forming region with dust and other things in it, we know that when we look at it with JWST, we'll be able to peer through it and get a completely different view of the universe. And so I think there's definitely choices as to what's aesthetically beautiful in trying to choose what would be fun to look at.
Are there any discoveries over the course of the first 2 years of this telescope's life that have really impressed you or, been maybe a little bit unexpected?
JWST is revolutionizing all areas of astronomy. And while today's image is of distant galaxies, what really interests me the most is how planetary systems form and evolve, particularly around nearby stars. So just within the past 6 months, there have been a couple of really great pictures that have come out. One was an amazing image in the New York Times of an asteroid belt around the young star Fomalhaut, which was never seen before. And again, this is part of JWST's superpower of seeing in the infrared. It means that you could see warm dust, that was close to the star that you couldn't see with any of the observatories before. And a little bit more recently from that was been an observation of another young star called Beta Pictoris, which has 2 giant planets. And there's the discovery of a structure called the cat's tail, which is a filament of dust, which people think is created by collisions of comets in the outer part of that solar system. So giant collisions. But really, the images are beautiful and we love them. But really, a lot of the science that's done with JWST is with spectra. And if we look at the requests that come into the observatory for science that people want to do, about 3/4 of them are for spectra. And so following on that exciting Beta Pic result, there is actually a result of the discovery of a change in the spectrum of that particular target that told us that there was another giant collision that happened in that system. And that one actually was much more recent. It was like 20 to 30 years ago compared to the other one, which was more like 150 years ago. And then this one involved asteroids in the terrestrial planet zone instead of comets in the outer part of the solar system.
It's amazing that we can kind of glean this history of these star systems from all of this way away. There are those examples. There was an article I read recently about these kind of binary Jupiter-sized objects just untethered from stars, just shooting through space. And these stories are so fascinating, and I feel like it's really interesting that we finally have the capabilities to look out into the universe and actually find these things. How close would a terrestrial planet have to be to us in order for us to actually get information about its atmosphere? Because the further away it is, it tends to be easier to actually analyze the light coming through atmospheres of like larger, more gas giant type planets.
Astronomers today are pushing the envelope, and so they are trying to understand the atmospheres of terrestrial planets, even with James Webb Space Telescope. And they're doing it through the transit technique, basically looking at a star and seeing what it looks like when a planet is in front of it or behind it, right? So, for example, if the planet is behind the star, you're only seeing the star. But if the planet is next to the star, for example, you get the spectrum of both of them. And by comparing the spectra when the planet is in the field of view and when it's not, you can try to learn something about what the atmosphere is made out of. There are some limitations to how we can do this right now with JWST. And so typically the most easy objects to study through this particular technique are planets where the planet is a fairly good fraction of the size of the star. And so that's driven people to essentially look at small stars, so low mass stars, M-type stars, to try to find and characterize terrestrial planets around them using the transit technique. And one of the very popular science themes right now is trying to understand what's called the cosmic shoreline. So these red dwarf stars that are low mass and small, they have very active atmospheres. And so essentially they have like coronal mass ejections. Like, if you think about our sun when it's active, like it's kind of like that, but on steroids. And so the thought is that these Earth-like planets that are next to these active stars might have their atmospheres blown off, right? But it's a start as a way to figure out, how to characterize atmospheres. So the cosmic shoreline is trying to figure out when there's an atmosphere and when there's not. But the goal, I think, for astronomers in general is try to understand Earth-like planets around sun-like stars. So our sun is bigger than these M-type red dwarf stars. And so they're less amenable to the transit technique. So future missions are looking to spatially resolve the planet away from the star and then to take the spectrum of the planet directly to see what its atmosphere is made out of.
We spoke recently on the show about the Habitable Worlds Observatory and other ground-based observatories that are coming online to try to help with this effort. But none of that would have been possible without this groundwork laid out by JWST. Are you and any other people on the team having a moment of celebration tonight because of this?
Oh, absolutely. I think it's just been amazing to watch the progress of the mission. It was really nail-biting at the beginning because the commissioning of the observatory was very complicated with so many moving parts and just people didn't know how it was going to perform. And now we know that it's doing spectacularly and it's really revolutionizing like all areas of astrophysics. And so, our expectation is that the observatory will continue to function well for many more years to come. The key consumable on board for the observatory is hydrazine. It's the fuel for the thrusters to station keep the observatory at L2. And initially, the observatory was designed for a 5 to 10 year lifetime. But one of the moments where we could have consumed a lot of hydrazine was the orbital insertion of the observatory into L2. But, the Ariane rocket gave us such a perfect ride that they used very little hydrazine. And so they've been able to preserve all that fuel. And so that extends the lifetime. And we think that it'll be like we're hoping for 20 years.
Oh, that makes me so happy to hear. 20 more years of JWST is just what we need to help us unlock the mysteries of the universe. So thanks for your time, Christine. And have a good time. Celebrate with everyone. You and everyone on the team, everyone around the world that's been working on this should be so proud.
Thank you so much.
In my conversation with Christine, she mentioned the Beta Pictoris system, a young star system about 60 light years away from Earth. She and her colleagues have recently detected evidence of an asteroid collision around this A-type star by comparing Spitzer telescope data from the early 2000s to new data from JWST. A few days after our chat, I had the chance to speak with her again and learn more about her favorite star system. The Beta Pictoris system is interesting to astronomers for a lot of reasons, but it's particularly compelling to people who study planetary formation. Although this system is only about 20 million years old, it's already home to 2 large gas giants. And closer into the star, this cosmic cradle is full of swirling dust, gas, and rocky debris that could be forming new terrestrial exoplanets as we speak. The complexity of this star system gets even more obvious every time we look at it. You wouldn't think that a lot can change in a star system over the course of just 20 years, but as it turns out, Beta Pictoris and its young family of worlds is full of surprises. Hi again, Christine.
Hi, it's great to meet with you again.
So, about 20 years ago, you were studying this star system, Beta Pictoris, with the Spitzer Space Telescope. And much like JWST, that instrument can see in the infrared. So this gives us a really great opportunity to compare these observations across over 2 decades of time. What initially piqued your interest in the Beta Pictoris system?
Beta Pictoris, it's a fascinating system, and it's one that we continue to revisit time and time again. And the reason why we look at it is because it's quite nearby. It's only 60 light years away, and it's very young. It's only 20 million years. So it's really a teenager in the sense of a planetary system. We now know that it's formed giant planets, but it's probably still in the process of forming terrestrial planets. So the new JWST observations sort of extend the baseline of our ability to study this system at mid-infrared wavelengths, to study what's going on, for example, in the terrestrial planet zone.
We've also found some other debris disks in this system, some that are aligned with the planets and even one that's kind of off kilter. When did we discover those?
Yeah, so those have been really fascinating. In general, we expect the disk to be, in the same plane as where the planets orbit around the star. But every so often, things don't quite work out that way. And we're not quite sure all the time why. For the majority of the systems, though, the circumstellar material, the dust, it's kind of like the dust that's seen in our solar system. So our solar system actually has what's called the zodiacal dust. And this is actually dust in the plane of the solar system that's kind of like where the asteroids are and closer. And it's an open, active area of research, like where does this come from? And so there are sort of two camps that have been going back and forth about this for, the past couple of decades. One idea is that you have comets and things coming from the outer solar system. And as they come into the inner parts of our planetary system, they release dust. And that dust sort of sticks around where it's released. Another possibility is that there are, of course, asteroids in the main asteroid belt, and that those asteroids, they collide with one another. And as they do so, they grind down and they produce dust, which can also be detected. And so the conversation in the community kind of goes back and forth every 10 years about which is the dominant contributor to the dust in our solar system. And I think right now it's the outer planetary objects that are winning, but sometimes it swings back around and people think that like the asteroidal dust contributes more.
These objects tend to be so far apart from each other. At what timescale would they have to be colliding with each other to produce enough dust for it to really matter for us?
I think it really depends on the system and how dense it is. So like how many planetesimals per like square kilometer or something there are. And that varies a lot over time. So when we look at our solar system, I mentioned how the asteroids are colliding and creating dust. But it turns out if you were to rewind time and look back when our solar system had an age of 20 million years or so, the asteroid belt then would have been much more massive than it is today, about 1,000 times more massive. And if there are more things and they're sort of still confined to the same region, it means that they bump into each other more frequently. So we think that, essentially when the solar system was young, there were a lot of collisions that created little tiny dust grains that we could then detect in remote sensing. But then over time, as we started to clear out the planetesimals, the number and density of them decreased. And so, the amount of dust produced also decreased with time.
I think what's really interesting about these more recent observations of the system is that we expect there to be dust, right? And we saw that dust present in the earlier Spitzer data. But then you looked back at it with JWST, and instead of finding the same amount of dust or more dust, you actually found that a lot of that dust was missing. Why were these spectra so different?
Yeah. So, this is a really great question, right? And I think it gets to a couple key things. One is that as astronomers, we always assume that we're not looking at anything at any special time. And so when we look at something at one time, we sort of expect when we come back, it's going to look mostly the same. But like with JWST, we have higher spectral resolution, we have better sensitivity, we have all these better things. And so we'll be able to study what was there that we saw in 2004 and 5, but just in greater detail. But as you pointed out, we actually saw something completely different, and it was so unexpected. I remember when I was sitting down with my students and we were looking at the data, we saw that the silicate features at 18 and 23 microns were gone. And I was absolutely stunned. The first thing that you always worry about is that you've made some sort of mistake with how you've processed the data. And so you have to go back and check and make sure that everything's right. And what was hard was it was the beginning of the mission. So there weren't a lot of observations that had been made that, could be compared to things that had been done previously. But over time, we started to see more and more results come out. And essentially, the JWST spectra, by and large, were always consistent with the Spitzer spectra. And so, at some point, we had to give up on like nothing's changed and be like, no, something really happened here. And now we have to really understand why.
Does that mean that, this was just kind of a special case and that system probably doesn't have that amount of dust in it at usual time periods? Because that could kind of recalibrate how we think about how much stuff is colliding in this system.
Yeah, that's a really open question. And the reason why is because we only have two observations. So we only have the one that was taken in 2004 and 5 and the one in 2023. And so we don't really know what happened between those 2 points. Like, the system could have continued to collide and create more and more dust. But then it just happened that when we looked at it again in 2023, that it was quiet. And so we actually need more observations to monitor the system in time to really find out what's going on.
You mentioned, too, that a lot of this dust had this kind of crystalline silicate material in it, which is really prevalent in terrestrial planets. We have a lot of it in Earth's crust and things like that. In this case, would that material be an indication that the thing that collided was more full of that, or the thing that it hit was more full of these crystalline silicates? Or is that just something that we should expect in a young system that's still forming its terrestrial planets?
So that's a really great question. So you presented two options, which is like the impactor or the target are made of this material, and that's how we see it when things collide. Another option sometimes too is that when you have these big collisions, you can have things get altered at very high pressures and temperatures, and it can change the chemical composition or the structure of the material. So one of my favorite ideas is that, another way to look for collisions is to try to see these products that are produced at high pressures and temperatures. So there have been models made for like what happens when asteroids collide in our solar system at these high velocities, right? And you can actually take silicates and alter them. You have chemistry that happens. And so you produce silica, which is SiO2, from the silicates, which are like, FeMgSiO4. And you can also in the process not only create silica, but you can also create maybe even silicon monoxide gas. And so some of these things, we have a model for them in that we see them on Earth. So if you've ever been to Arizona, there's Meteor Crater, which is a very clear impact site. And on the margins at the rim of the crater, there's materials like tektite, right? And so that's stuff that was created in the collision and then ejected onto the rim. And so you can see directly how stuff might have been, altered at high pressures and temperatures.
There are even some meteorites that we've found that have these beautiful kind of inclusions that are made out of this almost like silicate glass. They're my favorites. When you cut them in half and put a light behind them, those are my favorite meteorite displays.
They're so pretty. Absolutely. Yeah.
So we've kind of studied this inner disk. I'm assuming that this object is originating from closer to the sun in this system. I mean, both because of its spectral signature, but also because the dust in the system dissipated so quickly. Does that make sense? Or is it possible that this could have been a comet or something else that's kind of throwing us for a loop?
Yeah, there's a couple options. One is that, so you're right, that based on the temperature of the dust, we see the dust that disappeared, a good fraction of it had a temperature of 600 Kelvin. So that puts it deep inside the terrestrial planet zone within a few AU of the star. But, there's a couple of options. One is that asteroids are pretty close, like they're in the terrestrial planet zone. So an asteroid could have gotten in there and collided with something and created the dust that we see. Another possibility is what happened we used to think there was a period of late heavy bombardment in our solar system, but that idea has gone out of fashion. But the essential idea is that an object from the outer part of the planetary system coming into the inner part and colliding there. And then if it was a body from the outer part of the planetary system, it could be very ice rich and have a different chemical composition from an asteroid being involved in the collision. So you're absolutely right. When we look at the spectra, we see solid state emission features that tell us what the chemical composition of the dust is. And so we can kind of guess whether we think it's an asteroid or a comet. So, every indication that we have so far is that the body was really dominated by silicates. So olivines, pyroxenes, which astronomers use this parlance of amorphous versus crystalline. And crystalline just refers to the lattice structure of the molecules. So the crystalline forms are often called forsterite and enstatite. That's what astronomers say. I know geologists who really study rocks describe things differently. But they're all materials that we expect to find in the terrestrial planet region. So we really think that it's probably an asteroid that was involved in this collision that created all of this dust.
And do we have a good idea of how much dust it was? And can that tell us how big this object was? Because do we know for sure it was an asteroid and not two planetesimals crashing into each other?
Absolutely. So we can kind of guess by looking at the spectral signature that we see. So in this particular case, what happened is we can see not only, through looking at the shape of the spectrum, like what the temperature of the dust is, but we can also see the intensity of the radiation, which gives us a sense of how many dust particles there are. And so essentially we can back out how much mass and fine dust was created in this collision. So we think it's basically a moderate-sized asteroid worth of dust, so equivalent to Vesta. So something like a Vesta got busted up. But, in truth, it could have been multiple objects and, they got partially destroyed. And so not one thing that got completely destroyed. So we don't know the exact geometry. We just know how much stuff got released in small dust grains.
Plus, we know that this material is dissipated over the course of the last 20 years, but prior to that, it's not like we had a lot of spectra that we could compare it to. So do we have some idea of when this actually happened? Was it really close in time to that first observation, or do we not know?
Yeah, so we can kind of guess. And I think while we're not exactly precise, it's not a horrible guess. The central idea is that when we looked at the system, we saw dust that was 600 Kelvin. And then we also saw this crystalline forsterite dust, which was much further out in the system, maybe more like temperatures and distances equivalent to Saturn. And so the hypothesis is that what happened is that, the dust was created in a collision at one location, and then the star shines light. And that light exerts radiation pressure on the dust. And that's actually what's blowing the dust out of the system so that it gets removed and we don't see it anymore. So we can calculate how much time it takes for these little tiny dust grains to be removed from the location that we see them to out of the planetary system. And we think that it's, on the order of 20 years or so. And so we think it's really likely, essentially, just radiation pressure that's blown out the dust. There's a couple of details, like the smallest dust grains feel the most radiation pressure. So, those ones for sure, like if they're half a micron, would exit the field of view of the telescope in our observations. We could have slightly larger ones that are 1 micron or so in size. And in that particular case, they would be blown out not quite as far. They would only travel maybe 40 AU. And in that particular case, they're now, though, so far away from the star that they're cold and they don't radiate in the mid-infrared. And so we wouldn't see their spectral signature.
You said, too, in our previous conversation, we were talking about the penguin and the egg, but you brought up that not only have you detected this evidence of this more recent asteroid collision, but that earlier on in the system, maybe about 150 years ago, there's evidence of cometary debris and cometary collisions. How did we discover that?
Yeah, absolutely. That was another serendipitous discovery. That's one of the things I love about astronomy is you get so many unexpected things. So Beta Pic had been imaged from the ground in the mid-infrared. But the problem with imaging from the ground is that you have to look through the sky, and the sky is 300 Kelvin. It's bright and it's radiating. And so it limits the sensitivity with which you can see astrophysical objects. So this is one of the main reasons that we go to space, is so that we can be more sensitive. So these new observations were taken with JWST, the same instrument, MIRI, but now using what's called a coronagraph. With a coronagraph, what you do is you block out the light from the central star, and that's to help facilitate finding things that are faint that are around the star. So it could be planets, it could be dusty disks. And so in this particular case, they use the MIRI coronagraphs at 15 and 23 microns to block out the light. And they saw this new structure called the cat's tail. And it looks like a little filament. It looks just like a cat's tail, which is why it's been named that. But the big question was well, where did this thing come from? How do you get a weird structure like this, right? And so one of the people on the team, Chris Stark, he's a dynamicist. So he, likes to understand the orbits of different kinds of particles and how they get impacted by things. And so he made this really interesting suggestion, which was there was a giant collision in the outer part of that planetary system. So this would have then been at 85 AU instead of a few AU. And it would have been much longer ago, like 150 years ago instead of 20 to 30 years ago. And, essentially that what you're seeing is this filament that's been created by this collision, and it has a slightly different composition and grain size, which allows it to shine more brightly at 15 microns compared to 23. So it's got a different sort of characteristic to it compared to the background dust in the disk.
Was that collision's distance from the star what allowed it to make that tail, or do we expect that this more recent collision will ultimately end up with its own kind of filament structure?
My guess is that the two different collisions aren't related and that the cat's tail was through a very special set of circumstances that the more recent collision doesn't fall into. The cat's tail, is shaped by radiation pressure as well. So in this particular case, there are small grains that are also blown out of the system by radiation pressure that, so they're leaving the planetary system. And then it's kind of interesting, the little tip of the cat's tail where it turns over again, that's actually, we think, because the dust grains have actually left the influence of the host star and they're almost out in the interstellar medium. And so they're interacting with the interstellar medium. So there might be, for example, pressure from gas and dust in the interstellar medium, which then bends back that filament to create the little kink in the tail at the end.
We'll be right back with the rest of my interview with Christine Chen after this short break.
The Planetary Society is strongly committed to defending our planet from an asteroid or comet impact. Thanks to the support from our members, we've become a respected independent expert on the asteroid threat.
So when you support us, you support planetary defense. We help observers find, track, and characterize near-Earth asteroids. We support the development of asteroid mitigation technology. And we collaborate with the space community and decision makers to develop international response strategies.
It's a lot to do, and your support is critical to power all this work.
That's why we're asking for your help as a planetary defender. When you make a gift today, your contribution will be matched up to $25,000 thanks to a generous member who also cares about protecting our planet.
Together, we're advancing the global endeavor to protect the Earth from asteroid impact. Imagine the ability to prevent a large-scale natural disaster. We can, if we try. Visit planetary.org/defendearth to make your gift today. Thank you.
We were only just recently talking with someone from the Parker Solar Probe team about all of the infalling dust into our solar system from other star systems. And this is just another beautiful case of how this stuff just gets blown out by these really dynamic systems that are just forming. And there is so much going on in this star system. We've only been talking about asteroid and comet collisions and debris disks, but you're also finding some really interesting things about the two planets that we found in the system as well, right?
Absolutely. So they're excellent targets to go study. And there's been this very close association between the disk and the planets in this star system, because it was actually the disk that led to the discovery of the planets. So the disk was originally discovered through, again, this thermal heat that's radiated by the dust, way back in the 1980s by the infrared astronomical satellite. So we call it an infrared excess when a star looks brighter in the infrared than it should. And the hypothesis was that there was dust that was around the star that was getting heated up and then radiating that heat that people saw. And then close on the heels of that discovery in 1984, Smith and Terrell went to a telescope with a coronagraph. And that's how the disk was, really confirmed, was through imaging, blocking out, again, the light from the star. And then they saw this linear feature, which is the edge on disk. So people, of course, whenever they get better instrumentation, they have some favorite targets that we always go back to, right? And Beta Pic is one of them. And so time and again, we always go back there to see what new things we can learn when we apply our better instruments. So around 2000, Hubble Space Telescope looked at it with the Space Telescope imaging spectrograph, which also had a coronagraph on it. But it discovered a warp in the inner part of the disk, a tilt, which, at that time was hypothesized to be produced by planets. And it was actually follow-up of those observations that led to the discovery of the two planets that we know about now, Beta Pic B and C. So we now know that Beta Pic B is probably responsible for that warp. It's like got a semi-major axis of maybe 10 AU, and it's about 10 Jupiter masses. And so there's been this very rich history of studying the planet and the disk. So that sort of, there was this whole area of research, like, maybe 10 or 20 years ago, where people were very excited about seeing structures in disks. And what did that mean about planets? So, the typical thing was sort of like, how does the planet impact the disk? But I think where we're going in the future, and where I'm terribly excited about, is to understand like the opposite of that, which is like, how does the disk impact the planet, right? And so in the case of Beta Pictoris, what's happening is we know that there are these winds of dust grains that, clouds of dust that like travel outward through the planetary system. And if you can imagine like, being on a sand dune or something, and there's a good gust of wind and like, you get a burst of sand that travels down, you can imagine that like in this planetary system, that dust cloud might run into a planet. And then, the planet could incorporate that material. The thing is that it's not a lot of material by mass. So you're not really going to change how heavy the planet is. But the dust grains themselves are really fine. They're very small. And so they can actually stay lofted. There's a potential for them to stay lofted in the planetary atmosphere for a long time. And in that case, like you can imagine, you might have silicate clouds in some of these planets. And that's something that you could actually go and look for in the mid-infrared by taking a spectrum of the planet, looking for absorption features at 10 microns to look for silicate clouds.
And then I just imagine some kind of horrifying glass rain on these giant planets. I mean, 10 Jupiter masses is pretty large. And there's two of them with that mass in the system. I mean, what kind of star is this that can produce that?
Right. So this, you might guess based on this, that this star is more massive than our sun. So it's actually an A-type star, and its mass is, I don't remember exactly, but it's probably 1.5, 1.6 times the mass of our sun. So in a way, the whole planetary system is kind of scaled up compared to our solar system.
What kinds of differences are we detecting in the composition of the outer disk material versus the inner disk material? And do we know anything about the way that the planets are kind of like populating these disks with material?
Yeah, one of the key concepts for planet formation is the water ice snow line. And so when people used to talk about how planets formed in our solar system, right, it was noticed that Jupiter and Saturn, all the gaseous giant planets, they're beyond what's known as the water ice snow line. So the water ice snow line tells us like where water is in the solid phase and where it's in the vapor phase in our solar system. So beyond the snow line, you can get water ice incorporated into things. Inside, it gets destroyed because, it becomes too warm for like objects to hold on to it. And so this is critical for planet formation because the constituents of water ice are very abundant. And so it changes how much material is in the disk. So like the surface density of the solids. And it actually makes a difference of about a factor of 2. So in this way, it's much easier to form giant planets beyond the water ice snow line because now you can add in ices and things which boost the mass of the objects as you're trying to form them. So for example, in our solar system, we think that the planets formed through core accretion. And so you need to mass all of these solids to form the core before you can then accrete gas to form the atmosphere of the planet. So you're absolutely right. Like these are kinds of things that we're looking for in these external planetary systems is, for example, gradients in the composition of the underlying planetesimals. So are the ones close to the sun or the star, are they, rocky, kind of like the asteroids are in our asteroid belt? And are things beyond the water ice snow line? Are they like icy, just the way that comets are? And that's an open area of research. And we hope to solve that question with JWST.
Well, thankfully, this instrument is really powerful for analyzing even just the spectra of worlds. And you mentioned that the disk on this thing is pretty much edge on. So do we actually get a good opportunity to use the transit method to study the atmospheres of these outer planets?
These particular planets have fairly long periods. Beta Pic B is the outer one, and I think the period is about 20 years. So it's actually much more efficient to point at the planet when it's well separated from the star. It spends more time there. And then you can also integrate, stare at it for a long time to get good signal to noise. So this is not a system that is required to be studied by the transit technique. And actually, it's a system that people have looked for transit signatures from the planets, and they haven't been able to find them. Several years ago, there was a campaign around the world when they thought the planets were going to go in front of the star to look for that transit. And unfortunately, no transit was seen. There is this sort of concept of the Hill sphere. This is the area from which the planet can influence its local environment and like accrete things onto it. So there was a suggestion that they might have been able to see the Hill sphere for Beta Pic B, but there was no transit for the planet itself detected. So that means that like the planetary system isn't perfectly edge on. There's probably a little tilt to it to make the planet get, just miss going in front of the star.
And that probably means that, it's going to take a little more effort to try to figure out whether or not there's actually any planetesimals, like little terrestrial worlds that are already being formed in the system. Because we know there's 2 giant planets already, but, it's only 20 million years old. Who knows what is already formed there if we can't see it passing in front of the star?
And the other thing, too, is like, giant collisions like this, I think they're an indicator that there's still planet formation going on. And when we look at the history of our solar system, we think it took a good 100 to 150 million years or so for, things to sort of shake out and for the terrestrial planets, as we know them to kind of be there. So given that this one is so much younger, 20 million years, like it wouldn't be surprising at all if it's still forming its terrestrial planets.
Have we found any surprising compounds in these worlds or anything that kind of was interesting as we were studying these planets with the disks around them?
Yeah. So, one of the things that was really interesting that my student discovered was the presence of atomic argon gas. His name is Caden Worthen, and he's a graduate student at Johns Hopkins University. And we've been working together on this MURI MRS observation of Beta Pic. And I remember he was scrolling through the data. So the way that the data is formatted is it's kind of like a cube. And so you have an image and then at a whole bunch of different wavelengths, right? And so you can sort of imagine browsing through at different wavelengths to see how it looks similar or different, right? And I remember, when he found argon-2 emission, we were like, well, what is that? Like, why is there argon-2 emission here? This is clearly an argon line. And I remember telling him, well, maybe this could be a sign of activity from this star because, we see other kinds of activity from the star. And he went, okay, well, I'll think about that. And he went off and he did what's called a difference image, where you look at the system in the argon line, and then you look just outside the argon line and you take a difference of those 2 images, and then you can see where the argon actually is. And if it was just the star, we would have seen an unresolved point source where the argon emission was. But he actually saw extended emission. So he had discovered a brand new population of circumstellar gas, atomic gas, argon-2, which we didn't expect at all. So we went to a conference in March in Tucson called Dust Devils. It was a group of people who are, really excited about debris disks. And one of our colleagues there, Yanqing Wu, is really interested in understanding atomic gas. And we showed her the argon-2 detection, and she's like, that's really weird, right? And she's a theorist, so she went home and, she started trying to model it to figure out what was going on. And she came back and she said, this is really strange. This is telling us that there is way more argon in this system than we think there should be. It's enriched in argon compared to everything else by a factor of 10, right? If you think about the abundances of atoms in the sun. And so, she was looking at this in more and more detail, and she came up with this really interesting suggestion, which is that that argon gas is created by the destruction of icy planetesimals. So now these are ones that are much further out in the planetary system. And these icy planetesimals could have incorporated, a noble gas like argon into its structure in clathrates. And basically the collisions then would release the argon gas along with the destruction of the water and everything else. And so it's really fascinating because she was pointing out essentially that the abundances of, these light elements, carbon, nitrogen, oxygen, and argon, are overabundant and kind of in the same way as they are in Jupiter's atmosphere, right? And there's been a long discussion about how did Jupiter's atmosphere get to be the way it is? How did Jupiter form? And one idea is that it accreted icy planetesimals, and that's the source of the noble gas in Jupiter. So it's really fascinating how there are all these connections between different parts of the system.
I know that we're just talking about this one star system, but are there other star systems that are of a similar age that we can compare to as they're forming these worlds? And what can that tell us about the way that our star system formed?
Yeah, absolutely. Beta Pic is actually part of a group called the Beta Pic Moving Group. Stars don't form in isolation by themselves. They typically tend to form in groups. And so that's kind of what the Beta Pic Moving Group is. We think that there are stars that all formed at about the same time. And usually when you form stars, you get like a whole size distribution of stars. So you get like big stars, little stars. Usually the little stars are more common than the big stars. And so it gives us an opportunity to study how planetary systems form and evolve on two axes. So one of them is like to think about the solar system through time and to understand. We think that certain events happened in our solar system, that first the giant planets formed. They did so through core accretion. Then the terrestrial planets formed. Collisions were really important to this process. There was some planetary migration that cleared out the planetesimal belts. By studying things at a variety of ages, we can kind of get a sense for is that story of our solar system, is that common or is it rare, right? Because I think that's what we're generally interested in, is understanding, is our planetary system common or rare? That includes is there life like us in the universe? Because we don't always know what all the different parts of our solar system's history are that mattered to that story. And then the other axis that we can learn about, stars come in all sorts of different masses. And depending on the mass of the star, the environment around the star can be different. So for example, like our sun, we see light that comes off of it that's mostly kind of yellow. When it was young, our sun was more active. And so it had more stellar flares. It had a stronger stellar wind. And so those things can impact the circumstellar environment, the environment in which the planets are forming and evolving. When we go to for example, late type stars, these M-type red dwarf stars that are a fraction of the mass of our sun, this is right now the favored place for people to look for terrestrial planets. But they impact their environments in different ways. They have much stronger stellar winds. They're flaring much more frequently, all the time. And so, we think that they have the potential to almost strip the atmospheres off of their terrestrial planets, which would make them very different environments for life to be in compared to the Earth. And so this is part of what we're trying to understand is, where is that so disruptive that it prohibits life? And, we really need to be around a solar-like star. And then if you get to really massive stars, instead they radiate a lot of ultraviolet radiation, very high energy radiation, which also could be damaging. We know how the UV damages, for example, our skin cells and causes cancer and stuff like that. And so those may not be, ideal environments either. And so I don't know if maybe our sun is somehow in this sweet spot where the radiation from it isn't so damaging that it allows life to flourish.
And that's really challenging because terrestrial worlds of the size of Earth are so hard to spot around giant stars. So studying that angle on it is a little difficult. And on the other end, as you said, these worlds might have their atmosphere stripped by smaller stars that are still in their active flaring days. So that puts us in a weird place. But thankfully, we've got some really awesome upcoming telescopes that are going to have some really powerful and fancy new coronagraphs that will allow us to see these even more. And we've seen just how powerful coronagraphs as a technology are just through this story and what it's allowed us to see just in this single system.
Absolutely.
Yeah. looking forward to that. I know we all have to wait 20 years for the Habitable Worlds Observatory,
Yes.
but we'll get to test the new coronagraph technology on the new Nancy Grace Roman telescope. So it's going to be a really exciting few decades coming up in exoplanet detection and analysis, because we're only just beginning to have the tools to do this kind of thing. JWST has completely blown open the doors on this whole realm of science.
Absolutely. Yeah. And being at Space Telescope Science Institute, which is the home of JWST, we're all super excited there's a new Director's Discretionary Time program that's been approved. So this is a large program that was designed by the community. And the key question that it wants to look at is atmospheres on terrestrial planets using the transit technique. And so essentially 500 hours of JWST time is going to be devoted to looking at these terrestrial planets around M-type stars to find what they're calling the cosmic shoreline, like where there is an atmosphere and where there isn't an atmosphere, to really understand the impact of a star on its environment. Yeah.
I know that telescope time is super limited with JWST. There's so many people that want to get their hands on that data, and rightfully so. But you're one of the lucky ones who has some dedicated telescope time. Are there any other things that you're looking forward to observing in the future, or do you have follow-up observations planned for Beta Pictoris?
So I love Beta Pictoris. I think it is my favorite planetary system, hands down. But one of the large open questions for me in planetary system formation and evolution is about water in planetary systems. And, how common is it? I would say that right now we don't really know, because water is relatively difficult to study. Most of our observatories are on the ground. And so that means we have to look through Earth's atmosphere to try to study them. And so you can get confused between what's astrophysical and what's in the Earth's atmosphere. And so this is one of the great things about going to space, is now you're above the Earth's atmosphere and you have no confusion about what's from the Earth and what's from your astrophysical source. So one of the things that I'm doing that I'm super excited about is looking for water in other planetary systems. So we've already had reports and hints of water in other planetary atmospheres. So my student Caden Worthen found water in the Beta Pic planetary atmosphere. And, people have essentially been finding water in lots and lots of places in like brown dwarf and planetary atmospheres. But in this case, what we're looking for is trying to understand like where that water could have come from, right? So one possibility is that we have comets and Kuiper Belt objects in our solar system. And one of the outstanding questions for the Earth is, where did Earth's water come from? So the leading explanation today is that it was actually acquired from the outer part of the asteroid belt. And this is because we think that the Earth formed dry, that it was too warm here when the Earth formed for it to hang on to its water. So it had to have been delivered from somewhere else. And right now, the most promising candidate is the outer part of the asteroid belt. Although people have talked about other sources for water delivery in our solar system, such as comets. And you may see, over time, this sort of conversation about how do we tell where the water comes from? One of the diagnostics that people really like is the deuterium to hydrogen ratio, the DDH ratio. And we can measure that directly in mean ocean seawater. And we can measure it, for example, in comets and try and see if they're correlated to provide additional evidence that maybe that's the place where the water came from. So I'm really interested in these other reservoirs around other planetary systems and trying to see if their comets basically have water just like our own. We aren't 100% sure right now. I mean, theoretically, we think it should be there, but it's never been seen. And sometimes when we go and look with, for example, the Spitzer infrared spectrograph, we can look at the precursors to planetary systems, T-Tauri stars. So these are protoplanetary disks that have not formed their planets yet. And then Herbig stars, which are a more massive analog to T-Tauri stars. And we see in that case, for example, like that the stellar properties matter. So there was some really beautiful work done by Klaus Pontoppidan, who's now at JPL, that showed that water was prevalent in the terrestrial planet zone in these protoplanetary disks. So I don't know, maybe they could have held on to some water, but they found that, for example, in higher mass stars, like what Beta Pic, turned into, that they were relatively dry. They had more trouble finding water. So again, this is the story where like the environment of the planetary system matters, like what the host star does matters. So yeah, I'm really excited to follow the trail of water, to understand how water gets into the terrestrial planet zone, just to put our solar system into context, like how common, how rare is it?
Yeah, once we have enough data from all of these different systems, then we can start taking guesses at what systems might be better for worlds like Earth, which ones might have water. I feel like we're just at the beginning of this whole realm of comparative planetology and the formations of systems. And it's kind of unfathomable how much we're going to understand in the next few decades versus where we are right now. If anyone out there is listening and thinking about getting into exoplanets, now is your time. Please do it right now.
Absolutely. It's a great area of study.
Well, thanks for joining us again to tell us more about this system, and good luck with all of your upcoming observations, because this is some pivotal stuff.
I'm super excited, and thanks for having me today. It's been a pleasure chatting with you.
Now, let's check in with Dr. Bruce Betts, our chief scientist at the Planetary Society, for What's Up. Hey, Bruce. Did your dog get on the call again?
Yeah, he keeps doing that. And the other dog ran over because it's like, wait, I'm missing the conversation.
I got to speak with someone earlier about this asteroid collision that they detected in the Beta Pictoris system. And I just think that's so ridiculous that we're not just at the phase where we can study asteroids in our own solar system and actually accomplish planetary defense missions, but also detect asteroid collisions in completely separate star systems.
It's amazing. The things that we determine even at distant planets in our solar system is amazing. But when they're able to determine there was asteroid collision, dust cloud, dissipation of dust cloud. I mean, of course, they could be wrong, but they're probably not. But more data will tell.
It's cool too, seeing the evidence of that crazy, hectic dynamicism that would be in an early stellar system, because this is only 20 million years old. Right? It's a very young system that's still forming all of its planets. So seeing that we have that evidence of these collisions is pretty cool.
It is very cool. And I love how you've been in this field so long that you now say things like, it's only 20 million years old. Without even
the
batting
scales
an
of
eye.
Stars.
No, it's so true. It's just, I enjoy that.
I wonder what our solar system was like at 20 million years old.
It was dangerous as all hell. So early on, there was that whole sun forming thing, but then you had the leftovers flying around, and there was a much higher density of stuff, to use the technical term. And that stuff would collide, and big stuff would collide with big stuff. So that's why you had things like the impact into the proto-Earth that formed the moon and changed the Earth, rather, and all these other large impacts that we see on the older surfaces in the solar system, like the moon and Mercury, Mars, huge basins from where very large objects collided after those had formed. So it was crazy.
It's cool that we can see this visual evidence of these impacts on the more terrestrial and rocky worlds, but in the outer solar system, it gets a little more dicey. It's harder to tell, but there's a good chance that something hit Jupiter really hard, at least, because it's got that fuzzy core situation going on.
You had all sorts of big impacts that affected things. You've got, we think, that's why Venus is a weirdo with its rotation the opposite direction from everyone else in the solar system. You got Uranus tipped on its side, and that was after they mostly had already formed from things of similar size running into each other.
Yeah, another cool thing about this detection is the fact that the only reason we figured it out was because we had space telescopes for longer than 20 years, long enough that we could actually see this dissipate.
They've been doing that with ground-based data also for a long time, going back to glass plates and photographic plates from the big telescopes. So that's why when some things are discovered even now in the outer solar system, they'll find that they were on previous observations. They just weren't recognized because they were, in those cases, moving so slowly.
It's bonkers. Have you ever gotten to see those old glass plates?
I have seen them. It's been a while. Yeah, they're trippy.
Yeah, I got to go to the Carnegie Institute to see one of their glass plate collections once many years ago. And all I could think is, how did they ship these across the United States to other people to actually study them after they were being taken. Like, how do you store a glass plate and safely take it across the country before you have airplanes? Bonkers. I'm just so impressed with humans. But anyway, what's our random space fact this week?
It's personal. And I don't mean me. That's right, Sarah. Random space fact is about you this week.
What?
Well, okay, it's not really about you, but I didn't know if you knew. There's a crater named Sarah. Did you know this?
I didn't. Is it spelled like me, Sarah, or is it some other Sarah?
Yes. It is spelled like you, Sarah. I mean, only the first name Sarah. But it's Sarah, spelled like you, and it's on Venus. You are the proud owner of an 18.5 kilometer diameter crater on Venus. Congratulations.
That's where I'll build my space house, right before it melts.
Of course, it wasn't technically named after you, but I think retroactively we will name it after you. Don't worry, there's a Bruce, but it's smaller and on the moon.
At least we both get our own craters. That's nice.
Yeah, we get our own craters. Woo!
Woohoo!
Ah. Yeah, I couldn't find our last names, though. They aren't assigned to my knowledge. Although I have secretly in my mind named several features on Mars after us, so.
That just means that we need a Venus mission even more, because I need such a full-scale topographical map of this place that I can pinpoint where Sarah Crater is.
Oh, yeah, you can use, well, yes, we do need that, but Magellan data is plenty good enough to show Sarah to you.
Well, now I'm going to be Googling that right after.
Yeah, and it ties to the fact that I've used way back when, which is that almost all the features on Venus are named after women, with three exceptions tied to early radar observations.
That's so cool.
Yeah. There you go. That's it. That's what I got.
Sweet.
It's Sarah Day. Happy Sarah Day, everyone.
Thanks, Bruce.
All right, everybody, go out there, look up in the night sky, and think about who you'd name a crater after. Thank you, and good night.
We've reached the end of this week's episode of Planetary Radio, but we'll be back next week with even more space science and exploration. If you love the show, you can get Planetary Radio t-shirts, along with all kinds of other cool spacey merchandise at planetary.org/shop. Help others discover the passion, beauty, and joy of space science and exploration by leaving a review or a rating on platforms like Apple Podcasts and Spotify. Your feedback not only brightens our day, but helps other curious minds find their place in space through Planetary Radio. You can also send us your space thoughts, questions, and poetry at our email at planetaryradio@planetary.org. Or if you're a Planetary Society member, leave a comment in the Planetary Radio space in our member community app. Planetary Radio is produced by the Planetary Society in Pasadena, California, and is made possible by our members who've been working to defend the Earth from asteroid collisions for over 40 years. You can join us and help promote the study of star systems near and far at planetary.org/join. Mark Hilverda and Ray Paoletta are our associate producers. Andrew Lucas is our audio editor. Josh Doyle composed our theme, which is arranged and performed by Peter Schlosser. And until next week, Ad Astra.